Hello students, I welcome you all to my channel Engineers Academy. Do hit the subscribe button if you haven't done it yet. Now we are going to solve this problem which says that a package is dropped from the plane which is flying with a constant horizontal velocity of 150 feet per second. Determine the normal and tangential components of the acceleration and the radius of the curvature of the path of the motion. At the moment the package is released at A, where it has horizontal velocity of 150 feet per second, and just before it strikes the ground at B. So we have to find the normal and tangential components of acceleration and the radius of curvature at point A and then at point B. So as we can see that this package is following the projectile motion, so we can apply the equation of the projectile motion. So at A, let me write that at point A, as we can see that the velocity is horizontal, right? So we can say that the VAX, that is the horizontal component of the velocity, is equal to VA, which is equal to 150 feet per second, and there is no vertical component of the velocity, so we can say that VAY is equal to 0. Now we can say that the tangential acceleration is 0 since the package is moving with the since in the projectile motion the horizontal component of the velocity remains constant. So if the horizontal component of the velocity remains constant, so at A the tangential acceleration, this will be equal to 0, and the normal acceleration will be equal to, that is, VA square divided by rho. So as we can see that at A the acceleration of the package will be acting vertically downward, and that will be equal to G. So we can say that AN is equal to 32.2 feet per second square at A. So, and the tangential acceleration is 0. So we can say that this is equal to 32.2 feet per second square. So now we are asked to find the radius of the curvature. We know VA, so from this equation we can write that the radius of the curvature is equal to VA square divided by 32.2, and we know that VA is 150, so this is 150 square divided by 32.2. So this will give us the radius of the curvature at point A. So this is 150 square divided by 32.2. This gives us the radius of the curvature at point A is equal to 698.76 feet. So this is the radius of the curvature at point A, the tangential acceleration at point A, and the normal acceleration at point A is 32.2 feet per second square. Now for point B, let me write that at point B, to find the radius of curvature at point B, we need to have the path function. We need to have y as a function of x in order to apply that equation, that is, and the radius of the curvature is equal to 1 plus dy by dx square to the power 3 divided by 2 divided by d square y divided by dx square, that is the absolute value. So in order to evaluate this equation, we need to have y as a function of x. Now we can apply the equation of kinematics for the projectile motion. So now we know that x is equal to x naught plus VAX into t if we apply the horizontal motion equation, right? And this is our positive direction for the horizontal motion. So now if we define our coordinate system, so if I define my coordinate system at point A, so this will be my positive, the y direction, and this will be my positive x direction. This is my positive x, this is my positive y. So the package at A is at 0, 0, it is at the origin. So we can say that x naught is equal to 0. So we can say that x is equal to VAX is 150 So 150 into t. And similarly, if we apply the kinematic equation for the vertical motion, and this is our positive vertical direction, so we can say that y equals to y naught plus VAYT plus 1 divided by 2 GT square. So again, the package is at the origin, so x naught and y naught both are 0. This will become 0. VAY is 0 as well, so this is 0. This will become 0, so we will be left with y equals to 1 divided by 2. So G is minus 32.2. Since the positive direction of the velocity is in the upward direction, and the velocity is going to decrease in the upward direction, so if the velocity is going to decrease in the upward direction, the acceleration is going to be negative. So this G is minus 32.2, and this is into t square. So in order to have y as a function of x, we need to eliminate this t from this equation, and from this equation we can say that t is equal to x divided by 150. So now if I substitute this t into this equation, we will have y as a function of x. So now this is y, and 1 divided by 2 into 32.2 is 16.1. So minus 16.1 into t, and t is x divided by 150. So this is x divided by 150 square. So now this is y equals to minus 16.1 divided by 150 square into x square. Now this is y as a function of x. So now at b, we can find the radius of curvature. If I find dy by dx, now dy by dx is minus 2 into, we need to take the derivative of the x square, the remaining is constant, so that is 16.1 into 2 divided by 150 square into x. And we do not know the x coordinate of the package at point B. So if this is the origin, then what are the coordinates of point B from that origin? So we can say that, let's say that from this origin, the package is at a distance of x. Let's say this is x. Let's say this distance is x. So we can write that this is x, and the package has traveled a distance of 1500 feet in the negative y direction. So we will write that the y coordinate is minus 1500 feet. So now if we substitute this minus 1500 into this equation, so we will be able to find the x coordinate, since we have this y as a function of x. So now this is, we can write that y equals to minus 16.1 divided by 150 square x square. So from this equation we can find the x coordinate of the package when it is at B. We know the y coordinate. The y coordinate at B is minus 1500. Minus 1500 equals to minus 16.1 divided by 150 square x square. So minus sign will cancel out. So now from this we can find x square. This is x square is equal to 1500 into 150 square divided by 16.1, and if we take the square root, we will be able to find the x coordinate. So the x coordinate is the square root, gives us 1447. Now the x coordinate is 1447.85 feet. So now we know that when the package is at point B, it has traveled a distance of 1447.85 from its original position in the horizontal direction. So the x coordinate is 1447.85 feet. Now we can find dy by dx value at x equals to this. So now we can substitute this x value in this equation, so that will give us dy by dx. So dy by dx is equal to minus 2 into 16.1 divided by 150 square into 1447.85. So this gives me minus 2 into 16.1 divided by 150 square into 1447.85. So this gives me dy by dx equals to minus 2.07. This is minus 2.072. Now if we take one another derivative of this equation, we will be able to find d square y by dx. So d square y by dx square will be equal to this constant, right? So that is minus 2 into 16.1 divided by 150 square. So this is minus 2 into 16.1 divided by 150 squared. So this is equal to minus 0.00143. Now if we substitute this, value and this value, this is dy by dx value and this is d square y by dx square value, in this equation we will be able to find the radius of curvature at point B. So now the radius of the curvature at point B will be equal to 1 plus dy by dx. So dy by dx is minus 2.072 square to the power 3 divided by 2 divided by the absolute value of d square y by dx. So the absolute value will be the positive value. So this is 0.00143. So now let's find this radius of curvature at point B. So that is 1 plus minus 2.072 square to the power 3 divided by 2. So 3 divided by 2 is 1.5 divided by 0.00143. So this gives us the radius of curvature at point B equals to 8516 feet. So now at point B, now we need to find the normal component of the acceleration and the tangential component of the acceleration. So as we know that at point B, now let me remove these coordinates, and now we know that at point B the package will have the acceleration in the downward direction. So we know that the acceleration is again acting vertically downward, and that is acceleration equals to 32.2, and it is acting in the vertical downward direction, so that is in the negative y. So this is feet, and the tangential direction at point B will be acting like this. That will be the line which is tangent to the curve at point B. So this is this line is the tangential direction. This is the tangential direction, and this will be my normal direction, right? This is towards the center. This is my normal direction, and in the increasing velocity direction, this is my tangential direction, and the acceleration is acting in the downward direction, that is in the negative y direction. So now we can find the an and at component of the acceleration if we know the angle of this acceleration with the normal axis, or if somehow we find the angle of this acceleration with the tangential axis. So we will be able to resolve this acceleration into an and into at. So for that we have to find the angle of this tangential axis with the horizontal. So let me draw the horizontal axis. So this will be this surface is my horizontal axis. This is my positive x, and this is my positive y at B. So to find the angle of the tangential axis with the x-axis or with the y-axis, we can apply tan theta to dy by dx, right? So dy by dx, this dy by dx gives us the equation of the tangent to the curve, right? So dy by dx is the equation of this tangential axis to the curve, and the value of dy by dx at x equals to 1447.85 is the slope of this tangential axis. So from this we can say that the slope of the tangential axis is, which is equal to tan theta equals to dy by dx, is equal to minus 2.072, and from this we can say that theta is equal to tan inverse of minus 2.072. Now what is dy by dx? This is, if I make a triangle here, if we consider this triangle, so this is dy and this is dx and this is theta. So tan theta is dy by dx, right? So that is why if we take tan inverse of that dy by dx value, so tan inverse of minus 2.072, this gives us angle theta equals to minus 64.237 degrees, and the minus sign tells us that the angle is measured in the clockwise direction. So now we know that this is that angle theta, right? So, and this angle is measured in the clockwise direction, and this angle is equal to minus 64.23. So this tangential axis is making 64.237 degree angle with the x-axis or with the horizontal. Now as we can see that this acceleration is perpendicular with the horizontal, and this normal axis is perpendicular with the tangential axis. So if the angle between the horizontal and the tangential axis is theta, then the angle between this acceleration and this normal axis is that same angle theta. So we can say that this angle is that same angle theta. Now if this angle is 64.237, so we can resolve this a into its components, right? So this a will have one component in this direction, this will be an, and it will have one component along the tangential axis. So let me draw that. So this will be an, and this will be at. So now from this we can say that since the angle is made with the normal axis, so we can say that an is the cos component of the acceleration, of this acceleration, which is 32.2. So an is 32.2 cos of the angle, which is 64.237. remember that the negative sign with the angles only tells us the sense of the angle, which is measured in the clockwise direction. So an is 32.2 cos of 64.237. This gives us the normal acceleration equals to 14 feet per second square approximately, and then we can say that the tangential acceleration is equal to 32.2. This will be the sine component. So this is 32.2 sine of 64.237. So this is 32.2 sine of 64.237. So this gives us 29. So the tangential acceleration is 29 feet per second square. So this is the solution of this particular problem, which we were required to find the radius of curvature at point B and the normal and tangential components of the acceleration at point B. Now if someone asks us to find the velocity of this package at point B, so we can find the velocity by applying this equation. Now we know an is vb squared divided by rho b. So we know an and we know rho b, so we can find vb squared. So vb squared will be equal to an into rho b, and if you want to find the velocity vb, so we have to take the square root. So now an is 14 and rho b is 8516. Here we have determined this is 8516, so under the square root. So this is 14 into 8516. So this gives us vb equals to, vb is equal to 345.29 feet per second. So this is vb. So this is the solution of this particular problem. I hope this will help you in your learning. kindly subscribe my channel if you haven't done it yet, because many of the students, 72% of the students who watch my videos, but they didn't subscribe. So I will request you people that kindly subscribe my channel. It will help me a lot, and it will motivate me to solve such more problems from engineering dynamics and engineering statics.